At first, it sounds like something out of a science fiction movie. Robots building other robots. Machines capable not only of performing tasks, but of reproducing their own kind. It feels like a scene from a futuristic world we haven't quite reached yet. But the reality is, we're already there. Slowly, quietly, and almost invisibly, a revolution is taking place. One that's changing the very definition of what it means to manufacture, to design, and perhaps even to exist. The question of how robots are learning to build themselves is not just a curiosity. It's a glimpse into the future of artificial intelligence, automation, and possibly even evolution. For centuries, humans have built tools. Then we built machines to build those tools. Now, we're entering a new phase, where the machines themselves can conceive, assemble, and even improve the next generation. And the implications are vast. Let's start with the basics. How can a robot build another robot? It's a layered process. First, there's physical assembly, the ability of robotic arms or modular systems to construct components. But it goes deeper. More advanced robots are also participating in their own design. Through evolutionary algorithms, neural networks, and generative design, robots are now helping to figure out what robots should even look like. That means we're not just handing over tools, we're handing over creativity. Imagine a robot tasked with building a machine that can cross rough terrain. Instead of following human blueprints, it simulates thousands of variations. It tests different shapes, leg lengths, body configurations. It identifies what works and what doesn't. It adapts. Then it prints or assembles the best version. It's not just copying, it's evolving. This process is already happening in controlled environments. Researchers at MIT and other universities have developed robotic systems that use 3D printing to produce customized parts on the spot. These systems can be taught the building blocks, motors, joints, structural panels, and then design entirely new machines by combining these parts in novel ways. The robot becomes a kind of architect and builder rolled into one. Some of these systems use what's called modular robotics. Think of it like high-tech Lego blocks. Each module has a function: rotation, sensing, locomotion, and robots can snap them together into different configurations. These modules are built to be self-diagnosing and reconfigurable. If one part fails, another can take its place. If the environment changes, the robot can adapt its shape. And in some cases, these systems can even disassemble and reassemble themselves into new forms. We're watching the early stages of robotic self-replication. Not in the science fiction sense of robots building exact copies like biological reproduction, but in a much more practical and mechanical way. A robotic system with access to parts, plans, and energy could theoretically build a functional replica or even an upgraded version of itself. But how do robots know what to build? That's where machine learning steps in. With enough data, a robot can analyze previous successes and failures, learning from each iteration. This is called reinforcement learning. It's the same principle used to train AI systems to play games or drive cars. But in this case, the robot isn't just choosing actions, it's choosing forms. It's learning what works physically. A robot might try a dozen different ways to attach a limb, choose the one that moves most efficiently, and discard the rest. It might test different sensors to see which gives it the best feedback in dim lighting. Over time, it builds a library of smart decisions, and each new generation of machines can benefit from this accumulated knowledge. In labs around the world, this is already happening. In one experiment, robots are given a set of parts and tasked with building a new robot that can complete a specific challenge, like moving from one end of a platform to another. The robot tries out different designs, running virtual simulations. Once it finds a promising candidate, it begins physical assembly. It might use 3D printed limbs or attach sensors and motors in different configurations. Once the robot is assembled, it's tested. If it performs well, that design is saved. If not, the process begins again. This is evolution, sped up. What takes nature millions of years, machines can attempt in hours. And each iteration teaches the system something new. But self-building isn't limited to physical assembly. Robots are learning to design their own software as well. Through a concept known as AutoML, automated machine learning, AI systems are now developing other AIs. They analyze vast datasets, tune hyperparameters, and structure neural networks more efficiently than human engineers can. In a way, we're seeing not just physical reproduction, but intellectual self-assembly too. Of course, none of this is without concern. The idea of machines that can build themselves and improve themselves raises philosophical and ethical questions. Who controls the blueprints? What prevents a robot from creating something we don't understand or can't control? As with any powerful technology, safeguards are essential. But dismissing the field out of fear misses the bigger picture. Self-building robots could transform industries. In space exploration, we could send robotic kits to the Moon or Mars, where they would construct habitats, tools, and even other robots, adapting to the environment without human intervention. In disaster zones, robotic swarms could build bridges, shelters, or clear debris. In remote locations, they could maintain infrastructure where human crews can't reach. Even in manufacturing, this approach reduces waste, speeds up development, and increases adaptability. Instead of one-size-fits-all assembly lines, we get smart, flexible factories that can reconfigure themselves overnight. And the benefits extend to medicine too. Researchers are experimenting with microscopic robots, nanobots, that can replicate, self-assemble, or even evolve to perform specific tasks, like targeting cancer cells or repairing damaged tissue. In these cases, self-building isn't just efficient, it's life-saving. But perhaps the most exciting part isn't what robots are doing now. It's what they're learning to do. We're entering a phase where machines don't just follow instructions, they understand purpose. A robot may not have consciousness, but it can evaluate goals, test strategies, and optimize itself. That's not intelligence in the human sense, but it's a kind of mechanical wisdom, and it's evolving fast. As the boundary between builder and built continues to blur, we'll need to rethink our role too. In the past, we were the designers and robots were the tools. Now, robots are becoming co-designers. Eventually, they may become inventors in their own right. This doesn't mean humans are obsolete. Far from it. It means our role is shifting from the hand that builds to the mind that guides. We'll define the goals, set the ethical boundaries, and dream up the impossible. And robots will help us build it. So the next time you see a robot arm assembling parts, remember, it might not just be building a product. It might be building the future of robotics itself. Learning, improving, evolving. One algorithm at a time. Thank you for watching. If you found this fascinating, be sure to like the video and leave a comment with your thoughts. And if you're curious about the future of science, engineering, and the incredible things machines are learning to do, hit that subscribe button. There's a whole world of innovation waiting to be explored, and we'll dive into it together. See you in the next video.